Section 12.6 deals with surface area. And surface area, you're going to find, is very, very important in terms of certain applications. Okay, like for instance, finding flux, which is a rate of flow through a membrane. That's going to come up in chapter 13. Are there solids that you know of that we can find the surface area of? Are there formulas for certain shapes, certain solids that we can find? Like can we find the surface area of a box? Okay, so Ian's saying standard shapes. Okay, all right. So basically things that like we could we find the surface area of a sphere? Is there a formula for the surface area of a sphere, for instance? There is. Now maybe you don't know what it is, but there is. There does exist a formula. Okay. But the thing is that we have surface areas formulas for standard types of solids, like cones and spheres and cylinders and like boxes. But what if we wanted a more general way to find surface area? Okay. Well, section 12.6 deals with that. So let me go ahead here, and I'm going to give you a little guided tour of section 12.6, and then we'll look at an example. So, all right. Remember section 10.5, you learned that you could trace out a parametric surface in three-dimensional space, a parametric surface S in three-dimensional space. You could trace that surface out using a vector function of two parameters, u and v. Okay, so you have components x, y, and z, and you have a vector function of two variables. So like, for instance, a helix can be traced out with a vector function of two variables. Well, any solid, a sphere, cylinder, any solid, right? You had that on your MATLAB assignment, right? You used parametric. You had an interesting solid that was the result of you had to revolve something, but you had it. You've seen this plenty of times. You've seen this in homework in 10.5. You saw this on MATLAB assignment number 6. It's a big deal, right? And now we're going to use this concept to help us find surface area. So right off the bat, I'm going to go right to figure 1. And this is how many recall seeing this kind of scenario in the past, where you have parameters u and v. Here's figure 1. You have parameters u and v, and coordinates then uv coordinates over some region d. And if you were to set the one parameter equal to a number and set the other parameter equal to a number, the coordinate u sub 0 v sub 0 would be the coordinate where the coordinate in the uv plane where you fix the u and v values. That coordinate would correspond then to, when you take the vector function of that coordinate, you're going to be tracing out you're going to equivalently have a point p sub 0 on this surface. So again, the vector function of variables u and v traces out a surface, like you see there, that blue surface in the second part of figure 1. Okay, but remember, if you hold one variable constant, then the vector function becomes a vector function of one variable, and that traces out a space curve. Okay, so for instance, if you were to hold the u constant then the vector function, like set u equal to u sub 0, which they do up here, okay, in figure 1, well, the vector function of u sub 0 and v would trace out the space curve C1 on the surface, okay, because when you set one of the variables constant, your vector function is a function of one parameter, and that's a space curve. On the other hand, if you were to set the let's say it's the right way, set the variable v equal to a constant and let the u vary, well, you're going to trace out a space curve C2 on the surface. Now, when you hold both u and v constant, u equals u sub 0, v equals v sub 0, you get a point p sub 0 on that. That's the intersection of those two space curves. And you can, if you can find the derivative vectors, the derivative vector of r with respect to u and r with respect to v, which would be the tangent vectors on the surface to those space curves at the point p sub 0. Okay, so this is actually a very important for what we're trying to talk about here. And we've talked about this. How many recall us talking about this before, this scenario that they're showing in figure 1? How many recall us having this discussion before in class? Okay, excellent, excellent. And Ellie recalls it, Junu recalls it. And so, okay, well, how's this going to be useful for surface area? How's it going to be useful for surface area? Well, what we can do is, you know, those tangent vectors, those red tangent vectors are going to be very important. So remember how, you know, RU, the derivative vector r sub u is defined this way, okay, where you're integrating your components with respect to u, all right, and then evaluating at the u sub 0, v sub 0 parameters, those values. And then let me see here, the other, let me see, there should be one for r sub v. Oh, I guess that's up here. So that's how you would find that tangent vector. So r sub u and r sub v, you know how to find those tangent vectors. And that's going to then be the tangent vectors that you see in the figure. So again, how does this help us? Well, let's look at some surface here. In figure 2, hold on here. Figure 2, you see on the right a surface. And what they're doing is they're taking the surface, and it's not, you know, it's just some random surface. How can we find the surface area of that surface? Well, what we can do is we can take the surface and break it up into little patches. So think of the surface as like a quilt with patches on it. If we could find the area of each patch on that quilt and add up those areas, we would get the surface area of the entire quilt or the entire surface. Okay, and obviously if we, well, yes, so how are we going to, like that S sub ij, that's the ijth patch on the surface. How are we going to find the area of that little little patch? How are we going to find the surface area for that little patch? Well, what you can do, you see, is you can, in figure 3, you can approximate the area of the patch by a parallelogram. So the corner point on that patch, S sub ij, you can draw vectors, okay, that those two vectors that basically correspond to the sides of the patch, but of course it's not exactly equal to the sides of the patch, but you could do that. And then what you could do is, well, I want to say it's the right way. In figure B, now hold on here, in figure B, what they're doing is they have the area of the patch, but then they're defining a parallelogram, which is the vectors, the red vectors are those derivative vectors, okay? The R sub U and R sub V. And we could approximate the area of a patch that way by finding the area of the parallelogram whose vectors are defined by delta U times the vector times the derivative vector R sub U and delta V times the derivative vector R sub V. The reason you have the delta U and the delta V there is to control how large the parallelogram is. Obviously, if you pick more patches, you know, in the quilt and make the patches smaller and smaller, the patches are going to, well, the areas of those patches are going to get more well approximated by the areas of the parallelograms. You see on the bottom in this figure 3 in the B there, do you see how like the green parallelogram, how like in the bottom left corner, it approximates the surface area pretty good, but then it starts to fail, right, as you move away from that corner point. You see that? How in the beginning, those two tangent vectors, the parallelogram in the beginning approximates the surface area of the patch well, but then it gets worse as you move away from the corner point. Do you see that in figure B? Do you see what I'm talking about? In other words, what I'm saying is, I mean, if you were to make the patch smaller and smaller, do you see that even though the sides of the patch, that's right, like how it deviates from the green, that's exactly right. That's what I mean. Hold on here. That is exactly what I mean, Kunu. The patch, if you make the patch smaller and smaller, the area of the patch will be better and better approximated by the plane formed by those two tangent vectors. Okay, because it just will, you know, because the patch, even though it's on a surface and the surface changes, if you focus on a very small patch on the surface, that patch basically looks like a parallelogram, and you can approximate that surface area by the area of the parallelogram formed. But how do you make the parallelogram smaller? You multiply the tangent vectors by delta U and delta V. And so what happens then? What happens is, I want to find the right thing here. Remember, we learned how to find the area of a parallelogram. Okay, if you recall, back when you learned, how many remember this? When you learned about the cross product in section 9.4, you learned that you could approximate the area of a parallelogram by taking the absolute value of the cross product of the vectors that form two sides of the parallelogram. Do you recall that? Okay, in other words, hold on. Okay, so that's back in section 9.4. If we maybe it would be worth showing it. Let me go into 9.4. Let me go back here. One moment. Let me go back into. I'll come back to this. But let me bring up 9.4. It's like Back to the Future, right? Hold on here. I'm going to find it here. got to find it. Yeah. Okay, let me bring this up. So this is back, remember, how many recall in section 9.4, we talked about finding the area of a parallelogram whose with side vectors A and B, and the area of the parallelogram was equal to the absolute value of the cross product of those side vectors A and B. Okay, now it's ringing. Is it ringing a bell for you? And we actually showed why that's true, right? All right. Well, we're gonna apply this. Thank you, Ellie. We're gonna apply this now to what you see in section 12.6. So now let me go. Let me unshare here and go back into 12.6. Okay. Let me go back in. Hold on here. 12.6. One moment here. Okay, so one moment. Okay, so here we are, approximating the area of a patch by a parallelogram. Okay, and we'll make the patches small so the area, so the parallelogram basically basically the patch will be almost like flat when the patch is very small. Okay, even though the patch is on a surface that is like it's not a constant surface, it changes. If you concentrate your focus on a very small patch, that patch is basically gonna look like a parallelogram. Okay, and I don't know. I think of how many have heard of like the Fantastic Four with the monster, the Thing. Remember, there are 4 people in the Fantastic Four, the cartoon. There's all right, Ian knows what I'm talking about. You know, I think of that guy. You know, that guy, his arm is really a bunch of little parallelograms, right? His whole body, it's made of stone, but it's a bunch of parallelograms. Same kind of thing. Okay, I think that's a pretty good analogy. All right. All right. So now let's go to here then. What's the area of this? What's the area of this patch here, this green patch? Oh, okay, we know what that area is. And that patch has sides, vectors delta U, R sub U, and delta V, R sub V. So the area of the patch is just the absolute value of the cross product of those side vectors. But delta U and delta V are scalars, right? So by the rules for cross products, delta U and delta V can be brought outside of the absolute value of the cross product. Well, the delta U and delta V can be brought outside the cross product, and then they can be brought outside the absolute value. Right. So now, if we want to approximate the area, surface area of the entire patch. Okay, hold on, one moment. If we want to approximate the surface area, if we want to approximate the entire surface area that you see there on the right in figure 2, all you need to do is add up all these little approximations. Okay, and so for the surface area, so the approximation of the area of the surface is equal to the double sum of where you're adding up all the little areas of the parallelograms. So far, so good? All right, all right. And again, excellent, excellent, excellent. Thank you, Juliana, Madeline, Ian, and Hunu. And again, the delta U and the delta V are just factors that multiply the vectors so that it makes the parallelogram. The parallelogram is created by the two tangent vectors, but we make the parallelogram smaller by just taking little multiples of those vectors, and that's the delta U times the one tangent vector, and the delta V times the other tangent vector. So now, okay, if we take, what do you think is going to happen to this double sum as we sample more points and have smaller and smaller patches? What's the double sum going to become? It's going to be right. It's going to be a double integral. And this now then gets us to a formula for the surface area. And that's what you see here in this definition. Although it's called a definition, they call it a definition, but we really derived it, right? So if you have a smooth parametric surface given by that vector equation that traces it out, and it covers the surface just once, as U and V ranges through the parameter domain, then the surface area, okay, the area of the surface is given by this double integral. Okay, because in the Riemann sum, if I go up here a little bit, in the Riemann sum here, this double Riemann sum, the delta U and the delta V, okay, become a dA, right? I mean, if you had delta X and if you had delta Y and delta X there, you'd have no problem saying, okay, in the limit that becomes dy dx, hence dA, a unit of area, well, you know, a measure of area, differential for area, I should say. So, you know, okay, this makes sense. This makes sense. Hold on, I want to get this right. I'm having trouble getting it. Okay, so there it is. Now you have a formula. Are there any questions on this? We'll look at an example, but all right, so generally what I like to do when I do these problems, okay, these kind of problems, is I like to use this formula all the time, because this formula is going to work for any surface, a cylinder, a sphere, a paraboloid, anything, okay? But in the case where you have a surface, and the surface can be expressed as a function of two variables, like let's say a function of x and y, okay, as an example, then this formula you can actually have another version of this formula, but it only works when you have a function of two variables. And this is called a surface area of a graph. So let me show you that formula. Let me just get to that formula here. Yeah. So for the special case, when you have function z equals f of xy, okay, well, the parameterization of that surface is you can let x be x, y be y, and z is that function of x and y. Well, if you then have your derivative vectors r sub x, r sub y, remember x and y are the parameters now, okay, so x and y are your parameters. I don't have a u and a v, but I have an x and a y. The derivative vectors are as you see there. Okay, now why would that be? Let me just show you real quick here. Why would that be? Let me just show you real quick. Okay, so let's say r of xy is equal to x, y, and then a function of x and y. Okay, if you differentiate your um, your vector function of two variables with respect to x, okay, what are you going to get? You're going to get, what are your components going to be? What's the derivative of x with respect to x? A 1. What's the derivative of y with respect to x? That's 0. What's the derivative of f with respect to x? That's the partial derivative of f with respect to x. Okay. Similarly, the derivative vector with respect to y would be 0, 1, and then the partial derivative of f with respect to y. Okay. So now, given that, we'll go back to the book here. So this is how they get that. Now they wrote those derivative vectors in with like I, J, K components. I wrote it in component form, but you know where it's coming from. So what you can do, you see, is, I mean, we're finding a general formula here, wherein z is a function of x and y. You can do the cross product of those two vectors, and you're going to get then the cross product of the derivative vectors having components. The first component is negative partial derivative of f with respect to x. Second component is negative partial derivative of f with respect to y. And the third component's 1. Okay, well then the absolute value of that cross product vector, which is needed for the surface area formula, would just be this. Okay, and so this is another way to get it. And sometime, probably in the watch it videos or the master it, they'll probably have formulas like this as well. And I just wanted you to see where it came from. Are there any questions on that? All right, and again, let me emphasize, this formula, excellent, this formula works only if z is if your surface can be written as z is a function of x and y, you can use this formula. But if z cannot be written, if your surface cannot be written as a function of x and y, if it can't be written as what they call a graph, then you cannot use that formula. That formula won't work. Okay, you would have to use, in that case, you would have to use the more general formula here. And of course, you'll have access to those formulas on the exam, because as you know, I let you, I give you access to those formulas. So, okay, let us look at an example here. Okay, let me give you a moment to copy this example down, and then we'll go over the example. Okay, so what we want to do here is we want to find the surface area. Okay, let me just, this example is an example. I mean, there are examples in the book that are nice. This is an example that's not, this example is not one of the two examples that you see in section 12.6. This is, I'm adding this, my own example for a little more variety, to give you a little more variety. Now we want to find the surface area of the part of this paraboloid that lies inside this cylinder. Okay, so what can you tell me about that cylinder? What's the radius of the cylinder? Okay, right, you knew it has radius 3. Is the cylinder, does it go up and down, or does it go sideways? All right, I'm saying it goes along the x-axis. That's right. So think of a cylinder that goes along, that has the x-axis through its center. Okay, now inside the cylinder, okay, there is this paraboloid. This paraboloid, what axis goes down its center? The x-axis. So x equals y squared plus c squared. Well, you're used to seeing, you know, z equals x squared plus y squared. But we don't have, and that's an up and down parabola, right? In other words, what I'm saying is, and I'm trying to, you know, give a lot of detail in these lectures, okay? Because I know you look at the recordings from time to time. You know, here's the origin. This here, for instance, would be z equals x squared plus y squared. And for this paraboloid, okay, you have the z-axis there, right? Now, how many of you are like very, very, very comfortable with this paraboloid? Z equals x squared plus y squared. I mean, right away you think of it as a vertical bowl coming up from the origin. How many of you like, hey, that, I know what that paraboloid looks like, no problem. All right, good, good, very comfortable with that. All right, excellent. What I'm trying to say is, if you're comfortable with this paraboloid, okay, if you're comfortable, hold on here. If you're comfortable with, now hold on, I got to get my little thing here. If you're comfortable with this paraboloid, you should be equally comfortable with this paraboloid. Because this paraboloid here, x equals y squared plus c squared, the only difference is it's a paraboloid, it's a bowl, but it opens out in what direction? What direction does that x equals y squared plus c squared paraboloid open out in from the origin? It opens out in the positive x-axis direction. Okay, so what's happening is here is you have a paraboloid opening out from the origin in the positive x-axis direction. It has to be positive because y squared plus z squared is always positive, right? So x is always greater than or equal to 0, right? The paraboloid opens outward from the origin along the x-axis, but it gets stopped, right? It gets stopped by the cylinder that has finite radius 3. So in terms of a picture, here's a little picture. Okay, this is a little picture. So, you know, hopefully you see this picture in your mind, because sometimes it's difficult to draw three-dimensional pictures. But, you know, I just have it here. So I'm going to let you copy this. I'm going to let you copy this picture. I'm going to give you a moment or two to copy that, and then we'll talk about how to find the surface area. Okay, and the surface area, well, let me let you copy the picture down first. Okay, so now who can show me, who can shade in the surface area that we're trying to find? Who maybe with the pen can shade in the surface area, shade it in red or in blue? Blue's good. Blue's good, actually. Let's do blue. Okay, good. Thank you, volunteer. That's exactly right. Well, now hold on, hold on. Oh, wait, too much surface area. Too much surface area. That's all right. Let's try again. All right, Gnu, give it another go. Good. So that's the surface area we want to find. And right now, you know, before today's class, you wouldn't know how to find that surface area. But surface area like that's important, like for architecture and things of that nature. Okay. Um, so, uh, you know, not everything is a sphere or a cylinder, right? Or or a box, right? So here we're going to, now what do we need? What do we need? Well, we need the parameterization for this parabola. We got to have the parameterization. So, okay. And I'm going to show you two methods to do this. First method, which always works, is I'm going to use the standard surface area formula. So the standard surface area formula requires me to get the parameterization for that paraboloid. The paraboloid is x equals y squared plus z squared. So what I'm going to do is, well, I'm going to let y be y, z be z, and x will be y squared plus z squared. Once I have the parameterization, I'm halfway there because I can find my two derivative vectors. Okay. And also, well, let's see what's going on here. Let me give you a moment here to catch up. Let me know if you have any questions, and then we'll talk about this region D. Okay, so now why is, well, first of all, the region D is in what plane? Based on the picture, the region D is in what plane? It's a circle. In what plane? Is it in the XY plane? Oh, it's in the YZ plane. All right, now why would that be? Why would that be? And why is the region D a circle? Why is it a circle? Let's go back to our picture here. All the points on the surface, okay, have Y and Z coordinates, right? And the Y and Z coordinates are, for some reason, we're saying the Y, Z coordinates are restricted to this circle here of radius 3. Why? In other words, region D is all of this circle here up to a radius of 3. Why would that be? Why is, so in other words, we have parameters Y and Z, but we're saying that the Y squared plus Z squared has to be less than or equal to 9. Y squared plus Z squared has to be less than or equal to 9. Why is that based on the picture here? Every one of these points, okay, every one of these points here on the surface, every one of those points has an X, has an X and a Y and a Z coordinate, right? But we are saying that the Y and the Z coordinates, okay, the Y and the Z coordinates, there's a restriction on the parameters. Y squared plus Z squared has to be less than or equal to 9. Why is that restriction? Why is this restriction here? Maybe another way of asking it is, why can't Y squared plus Z squared be greater than 9? Why is that not allowed? Okay, good, Ellie. It'll go outside the cylinder. So the cylinder has radius 3. It's bounded, right? The cylinder has radius 3. So the paraboloid, when it touches the cylinder, it's stopped, right? It's stopped. And what is this cylinder here? Let me ask you this. Hold up for just a minute here. Hold up for just a minute. If you were to describe this circle here, which is the intersection of the paraboloid and the cylinder, okay, if you were to describe that, okay, how would you describe that? Well, you would say that, I want to be careful here. Hold on here. I don't want to get too complex here. But the point is, yeah, I want to be a little careful. I want to be a little careful before getting too deep. But the way I think of it, that helps me a lot, and maybe I'll use my stylus here, is all the points on the surface, all the coordinates on the surface have, you know, X, Y, and Z coordinates. But because the surface stops here, where the paraboloid intersects the cylinder, well, at like its most extreme, y squared plus z squared would equal 9. Okay, and that would be true for the points that lie right here at the edge of the paraboloid, where the paraboloid meets the cylinder. But for all of the other points, on the surface, y squared plus z squared would be less than 9. Okay, but if we then include everything, the points on the surface and the points on the rim here, where the cylinder intersects the paraboloid, y squared plus z squared is less than or equal to 9. And that gives us our restriction then that we see here on our parameters. Are there any questions on that? Who's feeling good about that? Who's feeling good? Maybe give me a thumbs up if you're okay. Yanu and Ellie and Charles. Okay. Let me just see here. All right, hold on. Hold on here, everybody. Madeline, Malik, all right. Gordon, how are you feeling? How's Gordon feeling? He's okay? All right, all right. Malik's good. And all right. Charles, Juliana, Madeline, excellent. Well, now it's time. Now, thank you, everybody. Now it's time to, I have my region B. Okay, I mean, let's think of the formula here. So the formula, I mean, here's the formula for the surface area. Here it is, right here. And dA, of course, dA in this case is, well, I'm not worried about dA. I mean, dA, I mean, I could use dz, dy, right? However, my region D is a circle, right? So maybe instead of using rectangular coordinates, I should use instead what kind of coordinates instead of rectangular? Polar coordinates. We should maybe try polar coordinates. So you see in the formula here, and I'm just trying to, you know, I'm trying to help you be comfortable with how to do these problems. I'm not going to commit to what variables of integration I'm going to use. Okay, but I've identified my region of integration, and I can decide on the variables of integration a little later. But right now, of course, I have to find the cross product of my derivative vectors. Okay, so I want to say this the right way here. So I say use this formula here. Okay, I say use this formula, but of course the formula I'm going to be using would be it's the same type formula, only I'm going to have the cross product of the derivative vector r sub y, with the derivative vector r sub z. Okay, so my parameters are y and z in this problem. So I'm not going to use u and v. I'm going to use y and z if you don't mind. Okay, so now what I got to do is I got to get this this cross product. And so we'll do that on the next page. We know what the derivative vectors are. We can go to the next page and figure out the cross product. So this is review, really. You've done cross products before using this approach. Let me give you a moment to copy down, and then we'll continue on. Okay, and while you're copying, let's see here. Marwan, how are you feeling with this? Are you okay with this? All right. Emma, how are you feeling? Are you comfortable with this so far? Good. Makes sense to me. I like that. Okay. Kino, how are you doing? You're doing good with it? Okay. No issues so far. Excellent. Noah, how about you? How are you feeling with this, Noah? Good. Good. Excellent. Excellent. Okay. Okay. So, well, all right. So we got our cross product vector, and now we have to take the magnitude or length of that cross product vector. We know how to do that. Okay. And so now our surface area is going to be equal to the double integral over the region defined by y squared plus c squared less than or equal to 9, where our integrand is the square root of 1 plus 4y squared plus 4c squared. That's our integrand. So you take these problems one step at a time. You have to. You can't do these kind of problems all at once. You have to dissect the problem into logical parts and move forward. Okay. Is it easier to juggle 2 balls or 5 balls? Which is easier, juggling 2 balls or 5 balls? 2 balls. So same kind of thing. There's a lot of component. That's right, Kino. A lot of components to the problem. Let me just, work it on each one of them, each part of the problem one at a time, and then. Well, now we are now at the point where we need to find this double integral. So if I were to say do dz dy. Okay, now of course I'd have to come up with limits, right? My upper and lower limit functions, and then the y values, the numbers. Can we integrate this integrand with respect to z? Is this easy to do with respect to with z? Not easy. Does anybody have any suggestions? I agree with Charles and Juliana. It's not easy. Must I integrate with respect to rectangular coordinates? No, use polar. That's right, Charles. That's right, Ellie. Okay, very, very good. So we're going to use polar coordinates here. Okay. So what we can do is, well, all right. So what would we use for polar coordinates? Okay, if we were to do, hold on here. If we were to do r dr d theta, then I'm going to let y equal something, and I'm going to let z equal something. What's y going to equal? Actually, let me go to the whiteboard. Hold on. Okay, hold on. Hold that thought. Hold that thought. Let me go to the whiteboard here. So here's my, and you'll want to put this in your notes, what I'm writing here. Okay, we'll go back to the you know, solution here, but this is actually adding a little detail to the solution. So y squared plus z squared less than or equal to 9, square root of 1 plus 4 y squared plus 4 z squared dA. Okay, so let's decide to use polar coordinates. If we do that, then I'm going to let y equal what now? Y will equal what? And z will equal what? So you're used to x and y being equal to something. But it's okay. We can let y equal to something and z equal to something. What are we going to let y equal to? Good. That's right. That's right, you knew. Y equals r cosine theta. Z equals r sine theta. Okay. And if I do that, the square root of 1 plus, well, if you don't mind, I'll write the 4y squared plus 4z squared. That's 4 times y squared plus z squared. Hold on. Okay, and if I do that, so I'm just looking at the integrand right now. Okay, becomes the square root of 1 plus 4 times y squared z squared. But what is y squared plus z squared going to equal? Well, in polar coordinates, y squared plus z squared, that's going to be r, that's right, Ellie, r cosine theta squared plus r sine theta squared. That will just equal r squared cosine squared theta plus r squared sine squared theta. And that's going to equal what? Well, r squared, because we can factor the r squared. Okay, and so I can make this a little nicer. Hold on. Okay, so sine squared theta right here, and this whole thing is just 1. So this is going to be r squared. So our new integrand is going to be 1 plus, kind of separate that out. Our new integrand is going to be square root of 1 plus 4r squared, right? 1 plus 4r squared. You know what I mean. Are there any questions on that? Okay, well then let's go back to the thing here. So here we left off. We left off here with our surface area formula. We're going to use polar coordinates. So therefore, this is going to be the formula, surface area formula with respect to polar coordinates. And we know that the region D was a circle centered at the origin with radius 3. So R goes from 0 to 3, and theta goes from 0 to 2 pi. We're going to have, I like to do my iteration step. How many like to use the little brackets like I have here to separate out the integral, the double integral when they compute it? How many like that? Doing that? Good. Juliana does. And it is helpful. I can tell you it's helpful. Okay, so really now, calculus 2 problem, I'm going to do a substitution. Let u equal 1 plus 4r squared. The limits change. You're going to have u limits now of 1 and 37. That's because, let's see here, 37 is 1 plus 4 times 3 squared, and 1 is equal to 1 plus 4 times 0 squared, right? And hopefully the steps you see there, hopefully the steps you see are, you know, okay. Let me know if you have any questions. All right, and all that's left now is to compute this integral here. Are there any questions before I go to the next page? Let me know when you're ready to move to the next page, and we'll finish this problem. And we're using method 1 in this problem right now. This is the method that formula always works. All right. Excellent. Okay, wonderful, wonderful. Let's proceed on then. Okay, so the final answer, the area of the surface, okay, the area of the surface is equal to, and this is the exact answer, and you know WebAssign wants that in homework and on exams. The area of the surface equals pi over 6 times the quantity 37 root 37 minus 1. Absolutely amazing. That's God's answer, right? So to speak. Well, not everybody believes in God, and that's okay. We all believe in what we believe. But what I'm trying to say is, I've heard it called that. It's basically the best answer possible, right? Best answer possible. If aliens were to visit us, they couldn't get an answer better than that, right? Because that is the best answer. I don't ask my students if they believe in aliens anymore, because very few students believe in aliens, you know. So, you know. All right. Well, maybe they will, Malik. Maybe they will. I mean, there's certainly enough. I mean, if you look at like videos and stuff, there's a lot of videos. I tend to, well, I got to be, you know, you know, I don't know, but you know, how many have noticed they've talked about UFOs in the news lately, right? Haven't they talked about that lately? It's kind of become a public subject. Used to be kind of secret, but they've talked about that lately, seeing one, you know, like that. But at any rate, now let's go ahead and talk about the second method. The second method, okay, the paraboloid, right? This is the, so let me just separate this. So a paraboloid, this is our paraboloid, x equals y squared plus c squared. That's where all the surface area is on, right? And you can write x as a function of y and z. In other words, x can be thought of as a graph based on y and z. And so the area of the surface area, would be equal to this formula here, which is just it's just like formula 6 in section 12.6, except instead of, you know, you have x and x as a function of y and z. Okay, and so if you work it out, okay, let me just put paraboloid here. Okay, if you work it out, okay, you take the partial derivative of x with respect to y. That'll be 2y. The partial derivative of x with respect to z will be 2z. And you wind up with the same integral. Isn't this the same double integral that we saw using method 1? That's the same double integral. It's just in method 1 we used the parameterization approach. We found the parameterization for the paraboloid, and then we arrived at this double integral. So the answer here is still going to be, it's going to be the same, pi over 6 times the quantity 37 root 37 minus 1. And this is section 12.6. You know, this is a nice, good example for you. So in these problems, they're not going to tell you, you know, I mean, when they basically say find the surface area. So there's a lot of, you just have to, sort of do a logical order in your steps. But when it comes time to integrate, you have to decide what the appropriate variables of integration are. Here, the variables, polar coordinates, were the right choice. You probably couldn't even integrate it using rectangular coordinates. Are there any questions before I stop the recording here for section 12.6? Okay, Yunu's good. Malik's good, okay. Wonderful. All right, let me stop.